Hi, my name is Tim Stutt, and I'm the Editorial Director for Laboratory Equipment Magazine. I want to welcome everyone to today's webinar sponsored by Buki. Learn to scale up your distillation process and save money. Today we're going to talk about how you can discover the most efficient way to scale up your evaporation process from a benchtop rotary evaporator to an industrial rotary evaporator. We will review available accessories and cover tips and tricks that will increase your distillation performance. We'll also provide you with application examples ranging from typical industrial applications to novel scientific findings such as solid supported evaporation or SSE. Following this presentation, we'll have a Q&A segment. I encourage everyone to submit your questions in the appropriate question section shown on your screen. This presentation will be available on demand within the next 24 hours on laboratory-equipment.com so that you can view it again at your convenience or share it with others. I'd like to thank today's sponsor, Buki, for their support of this webinar. Our speakers today are Dr. Daniel Meyer and Jeff Reed. Dr. Daniel Meyer is the application chemist at Buki Labortechnik, headquartered in Switzerland. His major tasks consist of experimental work in the laboratory, product training, and customer consulting in the field of industrial evaporation. In addition to his work experience in the environmental lab technology section, he continues to provide university-level lectures regarding process technology. He received his BSc, MSc, and PhD degree in chemistry from ETH Zurich. Also speaking today is Jeff Reed, who is the product specialist for the evaporation segment at Buki Corporation in the United States. In his role, Jeff specializes in benchtop, industrial, and parallel evaporation. In his past experience, he has worked on the development of silica media for HPLC columns. He has worked in the scientific industry for 6 years on both the analytical and preparative side. And now, without further ado, let's begin our webinar by welcoming Jeff Reed.
Okay, everybody. So what we're going to talk about is ways to upscale your distillation process and save you money doing so. We're going to go over the basic scheme of a rotary evaporator, compare different distillation rates, why and how you should upscale, how to master your application, go over tips and tricks that's going to help you with your application, and this is most important, protect yourself. We're going to go over ways to protect yourself when you're using industrial evaporators. We're going to hop into an application section and then summarize everything up at that point. So the basic scheme of a rotary evaporator, you have the evaporating flask, which the solvent is held in liquid form in. That travels up the condenser in a vapor form and condenses from the condenser back down to the receiving flask. Now you see there's energy applied in the system and energy applied out of the system. The energy applied into the system is heat, and this is coming from the heated water bath. The energy coming out of the system is coolant, the coolant that's going through the condenser coils. You need the same energy in the system as out of the system to have an equal, efficient evaporation process, and we'll go over that shortly. So, different distillation rates. You can see our benchtop rotary evaporators, which have a 5-liter maximum capacity. Distillation rate of ethanol is 4 liters per hour. The R220SC, which is a 20-liter maximum capacity, has a distillation rate of 13 liters of ethanol per hour. The R250, which is a 50-liter maximum capacity, has a distillation capacity of 19 liters of ethanol per hour. So it shows anytime you scale up, you're going to increase your throughput. And this is mainly due to the fact that there's an increased surface area inside the evaporating flask. So why do you scale up? Well, if you're working in kilo laboratory, pilot plants, your sample volumes are usually roughly 20-liter sample volumes. At that point, that's considered industrial evaporators. You would need to scale up. You no longer could use benchtop rotary evaporators. Solvent recycling, major production applications. Again, you need an industrial evaporator. Usually it's 50-liter volumes, and you need something much bigger than a benchtop rotary evaporator. Now the question is, how do you scale up? This is very simple. The same parameters that are being used on your benchtop roadies, such as the vacuum pressure, the coolant sensor, the coolant temperature, the rotation speed, the water bath temperature, those parameters can be used. They correlate exactly to the industrial evaporator. So it's really just quite simple. The only thing you have to worry about is choosing the volume size of the evaporation flask. So let's say your starting volume is 10 liters. Well, then it makes sense to go with a 20-liter industrial evaporator. If your starting volume was 30 liters, then obviously you would have to go with a 50-liter industrial evaporator. So you take those two things in perspective, the starting volume, and just apply the same parameters that you've already used on your benchtop roadies, and you're good to go. Just always remember, you're working with a large amount of solvent. It means you got to comply to stricter standards, GMP, GLP regulations. If you're working in an EX-rated environment, make sure you have an industrial evaporator that meets explosion-proof standards. And we'll get into that shortly too. So how to optimize the performance? Well, one is rotation speed. You can see in this graph, with the increased rotation speed, it increases the distillation capacity. That's because it's increasing the surface area inside the evaporation flask. Now, that doesn't mean to max the rotation speed all the way up, because if you're working with a foamy product or a solvent that could bubble over, you'll just contaminate the receiving flask. So you want to use the most maximum rotation speeds you can that makes sense for your application. It might not be 180 rotations per minute. It may only be 100 rotations per minute, but you want to find out the maximum way to achieve that so it increases your throughput. Next is temperature difference. You can see with the increase in temperature, it increases the distillation capacity. Again, it doesn't mean crank the water back to 180 degrees Celsius, because if you're working with thermosensitive samples, that can't be done. At that point, you would need a gentle temperature on the water bath, and you would just need to manipulate the boiling point a little more with the pressure. So again, find out what your most efficient water bath temperature can be set to, the highest it can, without you destroying any bonds or thermosensitive samples you have. Next is the change in 20 degrees Celsius rule. This was actually invented by Buki. This should be applied to every rotary evaporator, any application. And what this is telling us is that the speed of evaporation needs to be attuned with the vacuum setting, which is the pressure, and the coolant setting. Okay, so the boiling temperature, which is also known as a vapor temperature, should be 20 degrees higher than the coolant temperature. This all makes sense in the next slide. So what we have here, the water bath temperature is set to 60 degrees Celsius. Okay, that means we want the vapor temperature to be set at 40 degrees Celsius. And how do you do that? You do that by fine-tuning the pressure setting. You fine-tune it so you have a vapor temperature sensor that reads 40 degrees Celsius. And then in return, once you get that, you need 20 degrees Celsius less than the vapor temperature on the coolant. That'll allow you to sufficiently condense down the vapors and collect the solvent. If this rule isn't applied correctly, you overload the condenser, you pull solvent into the vacuum pump, or maybe your throughput's not as fast as it could be. So it's very important to use this rule. It's called a change in 20 degrees Celsius rule. So we have two pictures showed right now. The picture on the left, you see the vapor level is 3/4 the way up the condenser. The picture on the right, the vapor level actually overloaded the condenser. Anytime you get a condenser overload, what happens is the solvent will start getting pulled into your vacuum pump, and eventually it will destroy your vacuum pump. And then it's got to go somewhere after the vacuum pump, so it goes through the laboratory in the form of emissions. So it's very important to keep that vapor level 3/4 of the way up, and that change in 20 degrees Celsius will really help you do so. So if the condensation level is too low, that means you're not pulling enough vacuum or the water bath temperature is not high enough. So that means, again, you want it 3/4 the way up. If that's the case, you'll have no evaporation and a very slow process. If the condensation level is too high, it means that you're pulling too much vacuum and you're using too high a water bath temperature. At that case, you'll have emissions of solvent. You'll destroy the vacuum pump over time. I mentioned that earlier. You'll lose your solvent, and most likely you're going to have contamination. That's why one way to do this is to use a vacuum controller. Always find a way to control your vacuum. Whatever you do, you need to control your vacuum. It's very advantageous for many reasons. One, it allows you to achieve reproducible process parameters. It allows you to follow GLP and GMP regulations. Obviously, you're going to save a lot of time with the vacuum controller. You don't have to sit there and babysit it with a stopcock. You'd actually just twist the knob and let it evaporate. You're not going to have to worry about emissions in your laboratory, which is going to increase the health of your employees. You're going to have complete solvent recovery, which is more going green chemistry. If it's going out in emissions in the laboratory, sooner or later it goes out in the atmosphere. So you're actually collecting these solvents and you're disposing them of the proper procedure. Also, it minimizes noise. The vacuum controller, vacuum pump, and the chiller all communicate with one another, and it really eliminates the noise in the laboratory when you have all the units working as an all-one unit. And obviously, you're going to prolong the life of your vacuum source. And it's much easier, very easy to separate solvents, even with close boiling points when you're using a vacuum controller. Most importantly, it's going to prevent bumping. So let's get to more tips here. I'm sure a lot of people out there who's listening, you've evaporated foamy products before. And when that's happening, what do? When the foam gets to the distribution piece and right before the expansion vessel, you aerate it through the stopcock so the foam goes back down, and you got to babysit it. You got to keep doing it. Well, a very advantageous device to get, a very important device to get, is what we call a foam sensor. This goes around your distribution piece. So every time foam is detected, it's going to aerate the system itself, and the solvent foam is going to go back into the evaporation flask. It saves a lot of manpower. You don't have to babysit the industrial evaporator, and saves you a lot of time. So if you're working with the foamy sample, I really highly recommend this tool. Okay, I'm sure also people have to concentrate to a residual volume. They need maybe, let's say, 5 liters collected in their 10-liter receiving flask. So what do? You watch the system. Once you see it goes to that graduation line at 10 liters, you stop the vacuum pump, aerate the system, and lower the water bath. This tool here we call a receiving flask level sensor. This can be placed anywhere on your receiving flask, 3 liters, 4 liters, 5 liters, 7, 8, whatever. And as soon as it senses the collected liquid on the receiving flask, the vacuum pump's going to stop, the system's going to aerate itself, and the water bath is going to lower. So again, you don't have to babysit the system. I know I've worked in a lab, and it's tough to watch the systems if that's what you're doing. So these tools are designed to save you money, to allow your presence to be on other projects. Anytime you're working with powders, always use a fritted vapor duct. What this does, it allows the vapors to go through the frit, but it traps the powder before the frit, and it forces it back down to the evaporation flask. It's very, very nice device to use. Always make sure you use a drying flask. A drying flask is pretty much, it's an evaporation flask that has 4 baffles around it. Now, when the evaporation flask is rotating, powders inside of it they're going to bump up and down in the drying flask because of these baffles. That's going to cause the powders not to stick to the glass walls. So if you're working powders, make sure you have a fritted vapor duct. Make sure you have a drying flask. If you're recycling solvent, the most efficient way to do so is our continuous version. What it is if your evaporation flask goes dry, there's a reservoir that'll fill it up automatically, drain the receiving flask automatically. There's valves and sensors throughout it. So you put 20, 30, 50 liters of reservoir or some solvent, and you want that done. You just set up your reservoir, set up the system, and come back in a couple hours, and it's done. So anytime you're recycling solvent, continuous version. If you're performing any reflux reactions, it's very important to have a distribution piece that actually closes off the receiving flask. This will allow the solvent to go up in vapor form and come back into the evaporation flask so you can actually reflux and build up energy. And then when you're ready, you can open the valve and then collect into the receiving flask. So if you're doing reflux reactions, make sure you get a distribution piece that has a valve on it. This is one of the most important section. So please pay attention to this one. How to protect yourself. You need to protect yourself. You're working with large volumes of flammable solvents. You need to protect yourself. Always work with plastic-coated glassware. If implosions occur, well, you're going to be safe because it's coated by plastic coating. Always make sure you have a water bath that automatically lowers. There's some type of solenoid valve in there or something that will lower the water bath if something goes wrong. Same with the rotation speed. Let's say the evaporation flask wasn't on correctly and you didn't have the automatic stop. Well, it would have rotated, and sooner or later fly off and break. So you want your system to be safe. You want it to protect you. So you want something, make sure they have the automatic rotation stop, automatic fast lowering. Also, overheat protection. These water baths fit up to 20 to 50 liters of hot water in them. If things overheat, you want to make sure it's equipped with a trip switch, we call it, over temperature switch, and that'll actually shut off power to the water bath. Anytime you're removing an evaporation flask, 20 liters or 50 liters, it can be hard. So you need to make sure you feel comfortable with your system. If you have a tough time removing the evaporation flask from the system because of how it's mounted on the tower of the rotary evaporator, you may want to look into other systems. Make sure you find yourself a system that it makes you comfortable. If it takes you 10 minutes to get off the evaporation flask and you got to tug of war with it, you could drop it and it's dangerous. So make sure you get a system that is set up to help protect you. Always, if you can, always use an all-in-one control system. What this is going to do, it's going to provide you with the highest safety, less noise, and it's going to give you the most efficient evaporation process. Other safety devices is a protection shield. There's a shield that even if the plastic coating isn't good enough, you can put a protection shield around the whole glass assembly and even the water bath. Flask handler. So if, again, 20, 50 liter evaporation flask, if you don't have some type of handler, it means you pretty much have to bear hug the evaporation flask and move it to different parts of the laboratory. With the flask handler, it just sits on there and you can move it. And even more importantly, you can move it while it's still hot, so you don't have to wait for the water bath to cool down. You can actually lift it up because you're not going to be touching the evaporation flask. It's a very nice device to have on hand. if anybody's working in a ATEX compliant zone, EX rated environment, make sure your industrial evaporators meet the standards. I've ran in some cases where I saw industrial evaporators on the market that they said EX rated, but they didn't meet the standards. So if something happened, let's say something burned down, ATEX comes, they look at it, the bottom line is you won't get any insurance money. So make sure you're buying legit EX rated industrial evaporators if you're working in an EX rated environment. So let's jump in some polling questions just to keep see how good you guys listen to. First question, what is the most important variable to influence during the distillation process? And I'll give you guys about a minute. Okay, all right, very good. It looks like 53% chose pressure, 37% chose heat. Those are two very important variables. The one to influence is the pressure, though. The heat is, you can't do distillation without heat. So that's the most important variable, but the most important variable to influence is the pressure, which I got, it looks like 58%. Very good. Next one, what is one way to increase efficiency of the distillation process? Rotation speed, water bath temperature, an all-in-one system, all of the above. And again, I'll give you about a minute to answer. Okay, good. All of the above is the correct answer. Rotation speed, water bath temperature, and all-in-one system. Following those three, you can increase the efficiency of your evaporation process. I want to thank you guys again. At this point, I'm going to pass it on to Dr. Meyer, and he's going to talk more about applications with an industrial evaporator.
Okay, thank you, Jeff. This is Daniel joining live from Switzerland. I'm very proud to be here, and after this poll, I recognize that I'm talking to real specialists already here because you solved all these questions correctly. So what I will do now is I will present you 4 selected applications from different industries, also including research and development departments. But before starting, I would like to repeat the typical applications that Jeff has already mentioned. The first one is, of course, solvent evaporation. Second one is drying. Third one is distillation, can also be fractional distillation. Solvent recycling and solvent upgrade, we will have an example on this, and concentration. The typical evaporation rates with industrial rotovapors, Jeff mentioned it, it lies between 4 liters per hour for water to about almost 60 liters per hour for hexane. So we are not dealing with liters, we are dealing here with bigger amounts, tens of liters, or over one day, hundreds of liters. The first example is actually from a company located in Florida. This company is producing essential oils from orange, so an essential orange oil. And this food company, or we say food industry company, wants to upgrade its essential oil by evaporating off the ethanol from its product. By doing this, they add value to their product. They evaporate off ethanol, And the ethanol that is collected, they can even sell to liquor producers. So by doing a fractional distillation, meaning separating the oil from the ethanol, they produce two new goods, the ethanol and the orange oil, that have added value. So this is the first application. The second application is from a university located close to the headquarters here in Switzerland. It is obvious that solvents are a major expense, especially for organic chemistry groups, for inorganic chemistry research groups, but also for laboratory classes and practicals. So universities start to think, oh, how can they save cost? Yes, because here we want to save money. That's the topic of this talk. So what they do is they buy technical grade solvents in large amounts, because then it's cheaper. And they upgrade the solvent. So that's why it's calling solvent upgrade. They do it by distilling the solvent. And you see on the right side, you see an R220 SE located in the solvent upgrade lab of the Swiss Federal Institute of Technology in Zurich. And there, students can upgrade their solvents by themselves. Now, what is the impact of this? At least financially, there is a big impact. Here the example. You see on the left side the technical grade quality of 10 liters cyclohexane costs about $56. Then when you purify this technical grade by distilling it, you have a purified grade that costs on the market about $31 per liter. So you save for 10 liters about $250 by just evaporating it with an industrial evaporator. Now let's make a short calculation. Imagine that you do 2 batches of 5 liters of cyclohexane a day. That will take you about 1 hour to do so, and you save in 1 day $127. In 1 week you save almost $1,300, and when you repeat this 5 days a week and throughout the year, you save about $66,000 only for cyclohexane. So this is about saving money and upgrading it with industrial rotavapor. Now, the third application is somehow related to the last, but it's not solvent upgrade, it's solvent recycling. Also here, I have an example of a hospital, and in most hospitals there are pathology departments and histology departments. In these departments, tissue samples are analyzed, but before analysis they have to be prepared. And for the preparation of these samples, a high amount of solvent is needed. Yes, for example, the water is replaced in the cells by ethanol. That's one step of the sample preparation. Other solvents needed are xylene or toluene. So you need a big amount of solvents in the hospitals, especially in these 2 departments. So this hospital that you see on this slide is close to our headquarters again. They are using an industrial rotavapor, and this is actually running every day, this rotavapor. And in this hospital, they do about 26,000 biopsies a year, so 26,000 tissue analysis. For this analysis, they use about 30 liters of ethanol per day. Yes. And this is a small hospital. Now, let's make a small calculation here as well, estimating the cost of a liter of ethanol to be about $10 US. And from the people at that hospital, we know that the ethanol can be reused about 10 times. So by doing this, they save in 10 days about $2,700 in 10 days only. And remember that when you deal with organic solvents, you have also to dispose them correctly, and you save also a lot of money when you don't have to dispose so many organic solvents. So this was the application from the hospital. And now another one that is from academia, from research, a very interesting application that has been recently published in the scientific literature. And researchers thought that sometimes they have sticky products. As you can see on the left picture, on the left-hand side of the picture, you see some of the products sticking on the glass wall. And sometimes it can also be dusty. So they want to have a process aiming to have a freely floating powder. And they did this by mixing porous polypropylene beads with the compound and the solvent. So they mix the beads, the compounds, and the solvent together in an evaporation flask. They put this evaporation flask to the industrial evaporator and evaporated off the solvent. You see the process on the right-hand side of this slide. Now, when they have chosen the correct parameters for the evaporation, and this is not a one-day work, that was a tough work to find out here the best parameters, they could adsorb, and in this case it was an active pharmaceutical intermediate on these polypropylene beads. Now the advantage was in the end that they had a final product that was easily transportable, easily to storage, and also to reuse, because they could dissolve again the active pharmaceutical intermediate out of the polypropylene beads, or they could make a solvent swap from one solvent to the other. So we think that also this is a very promising application that is being done with an industrial evaporator. Some more information regarding this application. The same researchers, actually the researchers were from Sweden and from a pharmaceutical company, they did this process in a continuous manner. And therefore, they took an industrial rotavapor and they successively fed the solvent with the dissolved active compound in it and continuously evaporated the solvent, and like this slowly adsorbed this active component on the polypropylene beads. Again, they managed to have an easy to transport and store product which they could reuse, and it was of course also dust-free. So these were my 4 application highlights that I wanted to present you, showing you the broad range of application where the industrial rotavapor is being used. And Jeff, I would like to give back to you for a short summary of this presentation.
Okay, so things we've talked about. Always remember to fine-tune the rotation speed, fine-tune the water bath temperature, that both make sense to your application. Always apply the change in 20 degrees Celsius rule no matter what rotary evaporator you have, bench top or industrial. Make sure you control your vacuum. I'm telling you, I know it's an extra cost, but a vacuum controller is very advantageous to have. It's something you really need to do this process correctly with. Always protect yourself. I gave you a list of ways to protect yourself. certain features to protect yourself, make sure you look into them more, and make sure you're always protecting yourself. Remember, the process is always comparable to the results from a benchtop rotavapor. So when you're scaling up, you can use the same process parameters that you use on your benchtop on your industrial. Make your life a lot easier. Distillation rate increases with the increase of the evaporation flask size. Remember, that was due to the fact that there's more surface area inside the higher volume evaporating flask. Last, make sure you master your applications with appropriate accessories. For instance, if you got a foamy product, use a foam detector. If you're concentrating to a residual volume, look into purchasing a level sensor. There's products out there, accessories out there that will really help you fine-tune your whole application. So on my side, I guess that's about it. I guess Tim will take it from here. I just want to say thanks to everybody again.
Alrighty, thank you, Jeff and Dr. Meyer for your presentation. We now will move into the Q&A portion of this, and so please remember to send in your questions. We have a number of questions here that have already been submitted, but we can accommodate with the time that we have available. Still, we can accommodate a lot more questions. So. Going back to Dr. Meyer's example that he just discussed with regard to the hospital near his headquarters there, one attendee asks, what did the hospital do with the solvent contaminants? Were they just washed away with water after the distillation process? Dr. Meyer?
Yeah, that's indeed a very good question. So what is happening in this application is that ethanol is being distilled and collected in the receiving vessel, and the residues that will be in the evaporation vessel are disposed like they have to do in a normal hospital. Yeah, so they will not wash away this, so they are certain canisters where they have to do this. Maybe there is some blood in it or some medicine, so they have to put this correctly to dispose it correctly. Yes.
Okay. Is there another question here? Is there a study done regarding cross-contamination risks with solvent recycling in pathology and histology labs?
Okay, that's a very good question, actually. And I have to say I'm not a doctor in medicine, but what I know from discussion with the people in this hospital is that for the preparation of the sample, they can reuse the ethanol. There is no, to my knowledge, they did not do a specific study contamination-wise. But imagine having these organic solvents, at least for bacteria, or it is really not a nice environment. So this will die in this solvent. So at least we can rule out that. But to be frank, I don't know if there is. I would have to check literature and go deeper in that, but we know that they have experience for more than 10 years in doing this, so they must be really confident.
Okay, and another question here. We're drying organic salts from saturated IPA in a lab scale bookie. Our challenge is the salts foam on the walls into a solid mass. This traps some solvent and makes for difficult collection. Any suggestions?
Dr. Meyer, tell me if I'm wrong, but it sounds like a drying flask would probably be advantageous.
Absolutely.
Yeah, I would just use the drying flask. Make sure you can give us a call after this. Remember the part where I talked about the 4 baffles? That's going to cause, when it's rotating, it's going to cause the salts to bump up and down. It's not, so they won't have they can't stay on the glass surface long enough to actually stick to it. So I would say just look into a drying flask.
Okay. And that questioner already said thank you. Another question here. Can we distill solvent used for HPLC applications from the commercial technical grade using Rotavapor? I'm sorry, my thing, considering the huge price difference, the solvent in question is acetonitrile.
Okay, I will answer this question. It's a very good question because obviously the prices for HPLC grade solvents are very high, and here a single distillation is usually not sufficient to achieve this HPLC quality. Now, I can suggest a strategy. You can try distill it with a benchtop rotovapor, load it on the HPLC, and check the impurities. Yes, and the customer can decide if it's enough or not after one distillation. But I have to say that HPLC quality will not be achieved after a single distillation.
Alrighty. Another question here. Does a difference of the 20-degree difference that Jeff discussed hold good in virtually all distillations? Can you indicate some literature reference?
To all distillations with rotary evaporators, not your basic distillation setups, but with rotary evaporators. Can we provide something? Just shoot me an email. Tim, is my information given or?
Not at the back end. It goes to the regular Buki website.
Okay, what I'll do is I'll make sure that our marketing communicator shoots us out shoots everybody out an email, my email, and then we can look into that as well. But
okay.
So.
Okay. I have another question here. When distilling asphalt cement, is it necessary to introduce CO2 or nitrogen at the end of the process?
Dr. Meyer, I'm almost positive you do have to, correct?
Honestly, we have an application for analyzing asphalt, but the point is that there you need to have very high temperatures and very low vacuum.
Yep.
So there is a norm telling how you have to do this. And I cannot remember which gas it is, so I have to look up this norm.
Okay.
Yeah, so a lot of these, you're going to have our email questions. Some of these we just got to go back to our computers and look some stuff up. But once you guys get our emails too, please after this, please send questions still, and we can get you straightened up because I know that application pretty well. So.
And Jeff and Dr. Meyer will get copies of all these questions and be able to respond to you where specific aspects of your questions as well too. So we have your contact information when you registered. Okay. Another question here: are the accessories that can be used to crush or mill dried powders while in the evaporator? Are there accessories that can be used to crush or mill dried powders while in the evaporator? Some powders become bean-sized particles as they dry, and they hold onto some residual solvent and do not dry down.
I honestly, and Dr. Meyer, you tell me what you think. I think glass beads would work, right?
That would be a good opportunity to try this. Yes, I also agree, and maybe again the drying flask could be a solution for this.
Yeah, it sounds like you gotta get the powders bumping around so they break up. You could try a drying flask because then you don't have to worry about anything else, and see if that does the trick. If not, maybe try implementing like little glass balls in there that help break it up, or not even glass ball. Some type of plastic material ball.
Some inert material that is a stable inert material that will not react.
Exactly.
And maybe also try to vary the rotation speed. Yeah, if there is a slow rotation speed now and they just increase rotation speed, that might be the first step already.
Okay. And how would you compare a Buki evaporator to a solvent purification system?
Okay, I can take this question. Solvent purification system is quite open, so it can be a Buki industrial evaporator can be a solvent purification system. So what maybe the question is referring to a rectification system. So this can be compared as a rectification system with only a so-called one plate. That could be the correct answer to this question.
Alrighty. We're running a little bit lean on questions here, so if you have any questions, please, there's still quite a few people in the audience. Please send in your questions for Jeff or Dr. Meyer. Got another question here. Why only 10 recycles for the ethanol for the histology work in the hospital?
This must be, they have elaborated this process over so many years, so they stick somehow to these 10 cycles. More details I cannot give, but I can ask them and reply the one who asked this question more details and provide more details.
Alrighty. That looks to be about the last of the questions. Is there anything additional that you would like to let the audience know about, Dr. Meyer or Jeff?
I just want to say thanks to everybody again for joining in. We're going to be doing more webinars, and we're trying to do them to help you guys with different products to help you out, and anything we can do help on the application side, we're more than willing to do that. But that's the type of company we are. So thank you again for everybody.
Alrighty. Thank you, Dr. Myers. Thank you, Jeff. Appreciate your responses to and the presentation. And anybody, like I said, anybody who responded with questions or something, we will send those questions off to the speakers here, and they will get back to you with additional information like they mentioned. Again, this webinar will be posted on laboratoryequipment.com probably within 24 hours and probably by later today. And we thank you all for attending, and we thank Dr. Meyer and Jeff for their presentation.
Okay, thank you.